Welcome friends to my YouTube channel. Now yesterday's lecture I have told about the gravitational potential due to a thin spherical shell, and there I discuss the various cases, that is the depending upon the position of the point there will be different potential. Now in today's lecture I shall going to discuss the gravitational potential of a solid sphere. Okay, gravitational potential of a solid sphere. Okay, so we know that a sphere consists of large number of spherical shells. Okay, so this is the center. Okay, and this is the suppose point P. Say this is the distance r. Okay, so a sphere contains large number of spherical shells. Okay, so suppose their masses are m1, m2, m3, etc. So shells of masses m1, m2, m3. Okay, so we all know that outside a point the gravitational potential due to a thin spherical shell at a point outside is what? That is simply g into m by r, that we all know. Okay, so this is the gravitational potential at a point outside a thin spherical shell. So here obviously since the sphere consists of large number of spherical shells, the gravitational potential here will be the sum of the potentials of different shells. Okay, the sum of the potential of different shells. So what we can write? So gravitational potential at P due to the entire solid sphere. Okay, gravitational potential at P due to the entire solid sphere. Okay, so what is that? If you call it V, then we can write V1 plus V2 plus V3 dot dot dot. So what is it? The mass of the first shell is m1 minus gm2 by r minus gm3 by r dot. So what we can write? Minus g by r. This is sum over of I equal to 1 to n mi. Okay, so simply minus gm by r, where capital M is the mass of the entire sphere. Okay, entire solid sphere. Okay, so capital M is the mass of the sphere. Okay, so this is obviously for a point outside the sphere. Okay, so whenever we are talking about a potential due to a solid sphere, then we must have to assume that sphere has a large number of thin spherical shells. So potential at P is the sum of potentials of different shells. So that we do it. So the result is minus gm by r. Okay, so this is one thing. Now another thing that I am going to discuss today is very important in gravitation chapter, and you might all heard about this term. Okay, that is that you might all know this, that is Laplace's equation. Laplace's equation. Okay, Okay, you all know it. So in order to find out Laplace's equation, that means we have to consider a system of attracting particles. Okay, suppose this is a point P whose coordinates say is x, y, z, and we consider a system of attracting particle and let one particle of mass m, we take one particle of mass m, say whose coordinate is ABC, and this distance is r. Okay, so here we consider about a system of attracting particles, so there must be a potential of the system. So okay, so we imagine a system of attracting particle, so there will be a potential, so there will be a potential. Okay, now we take a observation point, say P, coordinate is xyz, and we take any one particle, say coordinate is ABC. So and if the distance is r, so we can easily know from coordinate geometry that r square can be written in this way. Okay, r square can be written in this way. R square, this is equal to x minus a whole square plus y minus b whole square plus uh, z minus c whole square. Okay, so just do one thing from which we can easily write 2 del r del x, this is 2 into x minus a. Okay, so from which we can easily write del r del x, this is simply x minus a by r. Similarly, we can write del r del y, this is simply y minus b by r, and del r del z, that is simply z minus c by r. Okay, so del r del x equal to x minus a by r, del r del y y minus b by r, del r del z z minus c by r. Okay, fine. Now we know that we consider a particular particle of mass m, so the gravitational potential of the entire system can be this. We have to take the sum of the different masses because we consider a system of attracting particles. That means there are many particles, so that's why we take the summation. Okay, so from which we can easily write del v del r, this is as sum of gm by r square. Fine. Okay, now what will be my del v del x? This can be written as del v del r del x. So del v del r is this sum of gm by r square, and del r del x is what? X minus a by r. Okay, so simply my summation of gm by r cube into x minus a. Okay, so del v del y, this is simply summation of gm by r cube y minus b. Okay, so what will be my del v del z? This is simply gm by r cube into, say, z minus c. This we can write. Okay, so simply this. Fine. Now let us do one thing. I cannot erase it because I am going to do the one term. Okay, this is del v del x. Okay, I am going to do it. Now what will be my del 2v del x2? That means we have to write del x of this summation of gm by r cube into x minus a. Okay, so this, fine. So just we do some differentiation. Now r again, x minus a whole square plus y minus b whole square plus z minus c whole square to the power half. Okay, so simply this is sum over gm is common for both terms. So take 1 by r cube fixed and do it, so there will be 1. And if you fixed x minus a and do it, that is r to the power minus 3 by 2. That means this is simply minus 3 by 2 into r to the power 5. Okay, and if you do this term again, so that will be 2 into x minus a. Okay, fine. 2 into x minus a. Okay, that is minus r to the power minus 3. That means minus 3 by 2 into r to the power 5. Okay, r to the power 5, and 2 into x minus a term will be there. Okay, so what we get, that is simply gm into 1 by r cube. This is minus 2 cancels, 3 into x minus a upon whole square by r to the power 5. Fine. Now similarly if we do it, that means del 2 v del y2, that means del y, we have to put this gm by r cube into y minus b. So if we do it, what will be the result? That is similarly, this is similar, just we write instead of x minus a, we write y minus b. Okay, the result will be same. Okay, oh sorry, this is gm. Fine. And if we write del 2 v del z2, again this is simply gm, this is 1 by r cube minus 3 into z minus c whole square by r to the power 5. Now if we add these two terms, these three terms, sorry, what we get? If we add, this is nothing but simple mathematical calculation. Okay, just you do differentiation. So if you add this, then what you get? This becomes 3 times. Okay, minus 3, this is also 1 by r cube, and this is what? X minus a whole square plus y minus b whole square plus z minus c whole square. So 3 into sum over of gm by r cube minus 3, but gm is common to both this term. Okay, so this is simply r square and there is r to the power 5. That means gm by r cube. So this is 0 and this is nothing but del square v. So we arrived at the result, and this is the famous Laplace's equation for potential. Okay, so this is what? This is 3D Laplace's equation. 3D Laplace's equation. That is one thing you have to remember, that you are trying to find out del square v. That means potential is involved here. So you have to consider a system of attracting particles. Okay, that means there is a force of attraction, so it can gives rise a potential. Okay, so this is three-dimensional Laplace's equation. So in our today's lecture I have discussed about the gravitational potential due to a solid sphere, obviously at outer point, and and a three-dimensional Laplace's equation. Okay, now in our next class I shall going to discuss the potential due to a solid sphere at a point inside the sphere. Okay, so if you like this video, then kindly subscribe it to get latest videos. Okay, thank you.